So I guess, yeah, sorry for the delay a little bit. I couldn't find water somehow. Anyway, so okay, let's get started. So last time we talked about concentration inequality, which was for some preparations for what we need today, or maybe the next lecture. And today we are going to go back to the uniform convergence. So recall that our goal was to do the uniform convergence. And we have proved some results. For example, we have proved that, I guess the first thing we had is that we say the excess risk is bounded by this uniform convergence, right? So we basically care about something like the soup of the differences. So guys, we have shown that the excess risk I don't know why something wrong with my, okay. Excess risk, this is bounded by, for example, something like L H star minus L hat H star plus soup L H minus L hat H, where H is capital H. And we have used this to get certain kind of uniform convergence result. For example, we have shown that for finite hypothesis class, we got LH hat minus L of H star. This is bounded by, I guess we have shown this technically, but this can be turned into excess risk bound. We have shown this is less than, this is less than square root ln H, roughly speaking, over N, if you ignore other log factors. And you can take soup over H in capital H. And also for hypothesis class parametrized by class with P parameters, we also have got something like L theta hat minus L hat. Sorry, I think there's something wrong with my notes. Let me take a quick note here. So we can get L soup theta in capital theta, L theta minus L hat theta. This is bounded by something like O tilde squared P over N. This is what we did like 2 lectures ago. So, and you can think of this, I guess we have discussed this briefly. So this quantity and this quantity, these are in some sense complexity measures of the hypothesis class. And this is generally the type of the results that we're going to get, right? So we're going to have something that decreases as n goes to infinity. And also there's another constant, which is, there's another factor, which is the hypothesis class, right? So basically, eventually you can say that, if n is bigger than the hypothesis class, then you can get non-trivial error bound. So the problem with these two bounds is the following. So the limitation, I think you can talk about different limitations from different perspectives, but I think the basic limitation of this P hyperparameter bound here is that it requires n to be much bigger than P, so that this bound is is small. So, and this is not necessarily feasible in many cases, and also this is not really what happens in reality, right? So in reality, like in many cases, n is smaller than P. It's quite often. It's not always the case, but it's pretty often. It's more often in a modern situation where you have a so-called over-parameterized network. By over-parameterized, I guess I will define that more carefully in the later course, in the later lectures. But basically, in the modern setting, when you have a deep network, your ImageNet has like 1 million examples, but your parameters could be something like 10 million or maybe 100 million. Sometimes could be billions. So Of course, this is not necessarily always the case, right? Sometimes you still have like n is bigger than p, depending on the situation. But generally, people found that it's useful to make your network, your p, very large. So definitely, it's not the case that you want n to be much, much bigger than p. That's definitely not true. So, and the reason, in some sense, why this is not capturing what happens in reality is that this is not precise enough, right? So, not precise enough in the sense that your complexity measure is, in some sense, two worst case, right? Your complex measure is measuring the complexity of all possible parameters with all possible models with p parameters, but you are not specializing enough to some special kind of models among all the models with p parameters. For example, you cannot, a trivial case, especially in the kind of more classical language, you cannot distinguish a sparse parameter from a dense parameter. You cannot distinguish, for example, you have a parameter class where theta has not one norm bound versus some hypothesis class where theta has some two norm bound. Right, so in either of these cases, the parameter p, the p will be showing up in your bound. So but not necessarily the b, the control of the norm of the parameters. So that's why we are looking for something that can be more precise, that can not depend on p, but depend on some more accurate characterization of the complexity. So today and next lecture, and next few lectures in some sense. So what we're going to say, our goal is to prove something like L theta hat minus L hat theta hat is less than something like some complexity of theta and over n. But this complexity measure could be more fine-grained than just a single number p. And this complexity measure could possibly also depend on distribution. So this complexity may depend even on distribution. Distribution p, right? P is the distribution of your data. So maybe for some distribution p, your complexity is smaller. For some other distribution p, your complexity is higher. And we are trying to capture the intrinsic kind of like difficulty of the learning problem. But of course, this is somewhat subjective because this depends on a little bit on what you believe that is happening in the real life, right? So if you believe that the real parameter is sparse, then you probably should have a complexity measure that captures the L1 norm of the parameters, right? If you believe that the ground truth parameters have other properties, then you probably should use a different complexity measure. But this is the general goal, and also the practical kind of like way of thinking about this is that you can think of the right-hand side as something that motivates your regularization, right? So the practical impact, I guess maybe, or the practical implication is that you can use this complexity of theta as a regularization. Because if you just optimize your model, right, you're going to find some parameter theta, and especially if you don't have enough data, you may have multiple global minima among the search space, right? So, but if you know that certain complexity measure will make the bound better, then you can actively find models with small complexity. So you can use this complexity measure on the right-hand side. Like you add this complexity measure multiplied by lambda to your training loss. So you get a regularized loss so that you are more likely to find the small complexity one which generalizes better. Okay, so I guess that's the basic idea. And so what we're going to do is that, so we're going to, today, the first part is we're going to talk about a weaker goal, right? Before we are talking about the uniform convergence, right? So this is our tool, right? So we want to prove that LH minus L hat H is small for all possible H. And And in the first part of the lecture, we're going to bound the expectation of this as some kind of like a weaker goal. And in the second part of the lecture, if we have time, we're going to bound it with high probability without expectation in front of it. And what's the expectation comes from? This randomness comes from the data, the training data, right? Because L hat depends on the training data, and the training data are random IID join. So that's why what's inside the expectation is a random variable that depends on the randomness of the training data, and then you take expectation of this random variable. And that's the goal. So we're going to bound, upper bound this with some other quantities that we think are more intrinsic and convenient for us to use. So I guess I need to start with some definitions. So this definition is called, this is a definition called Rademacher complexity, which is the main object we're going to focus on in this lecture. So the definition is, let F be a family of real valued functions. So far, F in this definition, F is just an abstract family of functions, and we're going to define a complexity for this family of functions F. And then we're going to say what functions of F we are going to care about. We care about actually the functions of the losses, the family of the losses. But for now, F is just the abstract family of functions, and you're going to define a complexity measure for this abstract family of functions. So let's say this family of functions that maps some input space, let's call it Z, to real number. And let P be a distribution over this input space Z. Then the average, the so-called, often you don't really necessarily have to specify its average Rademacher complexity, but technically it's the average Rademacher complexity of F is defined as the following. So this is R n sub F, where n indicates how many examples you have, how many training examples, how many empirical examples you have. Rnf is defined to be, you first draw some examples. You can think of this as training examples, IID from the distribution P. And then you draw some so-called Rademacher random variables. Recall that Rademacher random variables are just binary +1 -1 uniform. You draw sigma 1 up to sigma n, IID uniformly from -1, 1. And then you look at this quantity. You look at the soup over this function class capital F, and you look at the quantity, the average of sigma I F Zi, F from 1 to. So this sounds like a kind of like a pretty complicated definition, but let me try to interpret it a little bit. So in some sense, maybe first of all, only think about this quantity, right? Just think about what's inside this soup. So this is the correlation. You know, the 1 over n is just a normalization, which is not important. This is the correlation between the outputs of F, right? So the output of F is Fz1 up to Fzn, right? And some random variable sigma 1 and sigma n. Of course, if you just look at this, right, the correlation should be typically very close to 0 because you shouldn't correlate with random variables, right? But there is a soup, right? So you are first drawing the sigma 1 up to sigma n, and then you take a soup over F. So basically, you are saying that what's the maximal? So basically, this whole thing is the maximal correlation between F, the output of F, and sigma 1 up to sigma n after you draw sigma i's, right? So you first draw sigma I, and then you try to find something that correlates with sigma i's, right? You try to find an F such that it can output something that looks like the random things that you have drawn. So in some sense, if you have a high complexity, means that for most or for almost all, for most binary patterns, where binary patterns just means that you have the sigma 1 up to sigma n, there exists f in this hypothesis class such that the output on this family is similar to or correlate with the random pattern, right? So for any random pattern, if you draw it, then you can find post hoc of function f in this family class such that the output on this on z1 up to zn looks like the random pattern you have drawn. So in some sense, this is saying that how diverse the outputs you can have from this family of functions f, right? So if this family of functions f can map your z1 up to zn to any possible patterns, then this Rademacher complexity will be the largest, right? So for example, suppose every binary pattern can be somewhat output by this family of functions f on z, then you get the maximal Rademacher complexity intuitively. Any questions so far?
Is this necessarily a non-increasing function?
The question is this necessarily a non-increasing function of n? I think it should be, but it shouldn't be. But I don't think it's trivial to see why it's non-increasing. At least off the top of my head, I don't see a super simple argument. But I think you can prove it without too much effort. I think roughly speaking, how do you prove it is that you can, because you take the soup, right? So you somehow can. I think you can prove it by switching the soup with the expectation for one. For example, the last example, and then you got the, roughly speaking, the definition of the n-1 version of the Rademacher complexity. But maybe let me not do it on the fly, just in case I missed something, I got stuck. Right. So, but roughly speaking, I think that should work. Any other questions? By the way, I never got any questions from Zoom, so you should feel free to speak up. I just unmute yourself and ask questions. Sometimes I'm not even sure whether the Zoom is working.
Should f map to like -1 to 1, otherwise they have like unknown?
That's a great question. So f is not required to be mapped to +1 -1, and it's true that this can be unbounded, right? So this is actually sensitive to the scale of f, right? If you scale f by a factor of 2, then you're gonna have 2 times the Rademacher complexity. And this is actually somewhat useful in certain cases, which we probably will talk about later. There is a question. Okay, cool. So, okay, now let's see why we care about this. So why we care about this Rademacher complexity. The reason is that you know the following. So you know that, let me write down what is the theorem. Suppose you do this hypothetical experiment, you draw n examples from distribution P, and then you look at this quantity, the average of f of zi, I from 1 to n, minus the expectation of fz, right? This is kind of the quantity we have dealt with in the last lecture, the concentration, how much you deviate from your mean, but you take a soup here because you in some sense care about the maximum possible deviation post hoc after you draw the examples. If you look at this quantity, then this quantity is bounded by 2 times the Rademacher complexity of f. I guess to appreciate what the theorem is really doing, I guess it's probably time to say what kind of f we care about, right? So f so far is abstract thing, but now let's try to instantiate. So suppose you take f, the capital F, to be the family of functions that maps z, which is taken to be a pair of x and y, the input and output, and we'll map it to the loss function, the loss of x, y on the hypothesis H, for any H in the hypothesis class. So basically, this is the family of losses. For every model is a function, right? And given that model, and you get a loss function, right? Defined by the model H, right? So basically, this is the composition of the model function with the loss function, the two-dimensional loss function, right? The little l. So together, basically you get this is a map from the data point to loss of the data point, but you can vary what functions, what models you care about. So you get a family of losses. So in some sense, it's just a slight extension of the family of models in some sense. But here is about the losses. And suppose you care about this, you take f to be this, and you can see that the left-hand side is exactly what we was trying to bound, right? Just because fzi is loss of xi. I guess we write xi yi like this. Xi yi at h, right? So then the sum of the empirical sum is just the empirical loss, right? So 1 over n sum of fzi, this is just 1 over n times the sum of L of xi yi h. This is just the loss, the empirical loss of the hypothesis class, the hypothesis H, right? And the expectation fz is the expectation of the loss and where x and y are drawn from the distribution P, and this becomes the population loss, right? So that's why the left-hand side of this theorem is really just the soup over H, L hat H minus LH, something like this.
Quick question.
And you take expectation over the randomness of the data. So that's the weaker version of uniform convergence that we outlined in the beginning of the lecture, right? So, and you can bound this by the Rademacher complexity of this function class f, right? The Rademacher complexity of this family of losses. Right. So basically, the theorem is saying that the generalization error is less than the Rademacher complexity of f. Like, I think technical expectation of the generalization error. I think there was a question here.
Is this the soup of the absolute value of the difference?
No, there's no absolute value here. Yes, there's no absolute value. That's a great question. So there's no absolute value, and it becomes a little bit trickier if you add absolute value. I think if you add absolute value, first of all, you need a different proof, a slightly different proof, and second, you're going to have a different constant instead of 2. You're going to get probably 4. And the cleanest way to do it is that you don't do absolute value in this theorem. You do the absolute value in the outer layer. Actually, you don't even need absolute value actually technically, because eventually you only care about one side of the bound when you do the generalization error. So technically you don't even need absolute value anywhere. Right? Okay, so and if you really think about this R and F in this context, right? So for this particular F, what does it mean? It really means that how well the family of losses, right? So the losses of data and data can correlate with random pattern. Can correlate. Random pattern. So this is still sounds a little bit kind of like not super intuitive. We can further, for a simplified case, we can further simplify this a little bit. So, so suppose you have a binary classification. So suppose, let's say your y is between +1 and -1, and L is 0, 1 loss. So L of x, y, h is equals to the indicator of h of x is not equals to y. If they are not equal, you have loss 1, otherwise you have loss 0. And in this case, we can further interpret this a little bit more. So what you can do is the following. First of all, you rewrite this indicator into this form. We write it as a half times y minus 1 times h of x. This is assuming, here I'm assuming h of x is also in +1 minus 1. So by the way, what I'm doing here is to try to instantiate this into a special case so that you can interpret the Rademacher complexity more in a more intuitive way. And also this whole thing is also useful by itself as well. So when h of x is +1 minus 1, then y is +1 minus, and also y is +1 minus 1, then the indicator that they are different, you can write this as this. Because if y and h are different, then you get y hx is -1, and then the whole thing will be 1. And if y and hx are the same, then y times hx is 1, and then this quantity is 0. So you can just verify it. Right? So the reason we do this is we somehow make it more linear in y and hx. And then you can look at the Rademacher complexity. So the Rnf is this expectation of soup sigma I. Right, so, and let's plug in the loss. So here the expectation, so in the definition I have 2 expectations, right? So but now I put 2 of the expectation into one, like just you merge them so that the randomness comes from both the data and the Rademacher pattern. And you get soup over h in h. So you plug in this formula, a half times 1 minus yi hxi times sigma I. And now let's do some rearrangement. It's a very simple rearrangement. Plus 1 over n times a half sigma I. So here, this quantity, it's inside the soup, right? But actually it's a constant that doesn't depend on h. So you can put it outside of the soup. So you can technically write this, just because this sum of sigma I is a constant. And then, because now you can switch the expectation with the sum and get expectation soup of the first term and plus the expectation of this 1 over 2n sum of sigma I. And this term becomes 0. Oops, wrong. Oh, here. And this thing becomes 0 because the expectation of the Rademacher variable is 0. And so then we're only left with the first quantity. And if you look at the first quantity, then you realize that so sigma I is a random variable, right? So H yi sigma I has the same distribution sigma I, right? No matter what y is, right? So for even for y is 1 or for y is -1, they have the exact same distribution. So that's why you can replace yi sigma. Actually, you can also have minus here. That's still true, right? Because you anyway randomly flip the sign, right? So basically that means you can replace y sigma minus y sigma I by sigma itself. Still, you don't change the expectation, right? So you can replace this by maybe let's define this. I guess you can say the easiest way to check this. I saw some confusion. Easy ways to check this, you just define sigma I prime to be minus y sigma I, then you get sup 1 over n sum of hxi sigma I prime. But still, sigma I prime's distribution is still plus 1 minus 1 uniform and independent, right? So sigma I prime has the same distribution as sigma I, so you can just write this the same way as this. Sigma I. Okay, so what we have achieved here? What we have achieved here is that this seems to be a strictly simpler quantity than before. Why? This is basically the Rademacher complexity of the hypothesis class H, but not the family of losses, right? Before we were talking about the hypothesis class of the family of losses, and now you're talking about exactly the Rademacher complexity of the hypothesis class H. So basically, this is saying that for binary, I think I'm missing something. I'm missing a half here. Where is the half go? Yeah, I think I lost the half. Sorry. I think I lost. Oh, I have the half in the notes. It's just I forgot to copy it. So basically, this is a half times the Rademacher complexity. So what we achieved is that the Rademacher complexity of F in this special case of binary classification and 0-1 loss is equals to a half times the Rademacher complexity of the hypothesis class. So that's a slightly simpler, way of thinking about this, because what's this? This is basically saying that how well H can memorize the random label, right? You can think of sigma 1 up to sigma n as random label, and Rn is big when there exists a H in the capital H such that H of xi's is equals to sigma I. This is the best situation, right? This has the strongest correlation. So basically, if you can memorize all the random label with some hypothesis in your hypothesis class, that means your Rademacher complexity is the biggest, and that gives you the worst generalization bound. And vice versa, if you cannot memorize, then you get better generalization bound. Right. Okay. I see. Okay, that's a good question. Let me repeat the question. So the question is, sigma prime is equals to y times, actually there's a minus there. So, but it doesn't matter. So sigma prime is minus y times sigma I. But yi itself is random variable. So can we still claim that sigma prime has the same distribution as sigma I? Right. So that's a good question. So it's so technically, I think what you should do is the following. So if you are really careful about this, so there are two randomness, right? So one is from the x and one is from the sigma. So you first condition on the randomness of xi. Let's say that. So you first, in the first expectation, so basically, how do I say this? So you can write this as the following, right? So you condition on xi, yi, and then you look at the randomness of sigma I. Right. So now after you condition xi, then this is absolutely clear, right? So like for any choice of yi, right, sigma I and sigma I prime has the same distribution, condition on any choice of deterministic choice of yi. So then, so you do it inside, and then y is gone in your formula. So then you don't have to care about the outside. Does it make sense? Okay, cool. So sounds good. And let me kind of like so the take home away here is that the Rademacher complex of F is similar to the Rademacher complex of the model, and the Rademacher complex of the model is basically saying how well you can memorize random label, right? But there is a small caveat here, which is that this relationship is not always true. This relationship is exactly true for binary classification 0-1 loss, but it's not even true for example, some other loss function. So I think the intuition largely is still correct, but you cannot take this, literally or rigorously, like religiously for every situation. And in some cases, actually, there could be a confusion because there could be cases where these two are mismatched, especially if your loss function can do something differently. For example, your loss function could change the binary number to real number, or the loss function has other kind of properties, right? So, for example, your loss function is often nonlinear, right? So suppose you take exponential loss. So, and actually, they are in some sense like in the past, they were this kind of like in some extreme cases, you could some papers or some papers actually misinterpret this in some sense, I guess I'm just giving a warning in some sense. Don't like always apply this at every time without even thinking about it. The intuition is roughly true, but it's not exactly true at all time. I guess there will be a place where I'm going to mention this again, like in the later of the lecture, like in some of the later lectures. Okay, cool.
One question?
So, and by the way, and what we're going to do next is that we're going to prove the theorem. And just a small kind of overview for what we will do next lecture. So in this lecture, we're going to deal with this abstract measure, the Rademacher complexity, right? And you may wonder, probably some of you are wondering why Rademacher complexity is something measurable or something like that is useful, right? So we don't answer that today. We're going to answer that, in the next few lectures. So today we are just introducing this Rademacher complexity and say this is bounding the uniform convergence, and this Rademacher complexity is something intuitive. I hope you found that, right? So like it's talking about how well you can memorize labels, right? So it's something at least makes sense. And then in the next few lectures, we are going to instantiate this to more concrete models where you can bound the Rademacher complexity by something more concrete in the next few lectures. I got some. Oh, did somebody ask a question I didn't hear?
Yeah, I think a couple people chimed in. You answered my question in the meantime, but someone else might have a question still.
Yeah, sorry, I forgot to open my have volume on. Please ask questions. If you, now it's working. Okay.
Thank you.
Oh, actually, there is a question. What is the connection between the Rademacher complexity and the degree of freedom? Right. I think I assume by the degree of freedom, you mean the number of parameters, right? So, so I guess that's kind of like what we motivated in the beginning. So, using this Rademacher complexity, we will be able to prove more precise bounds than the number of parameters. So, probably so far you haven't seen that. I don't expect you to see that. But in the next lecture, we're going to see you can prove better bounds that depends on something more fine-grained than the number of parameters. I hope that answers the question. Please feel free to just unmute yourself and ask any follow-ups. Okay.
I have a, I guess, conceptual question. How do you generally think about the distinction between the hypothesis, the family of hypotheses versus the family of losses over them? To me, because they have the same cardinality, right?
they seem like a direct mapping between one. How do you distinguish, I guess, in your mind between those two? How do you think about them?
Yeah, that's a great question. So in my mind, they are very similar, except that yeah, I think this will be a little bit more explicit in the next lecture, or maybe 2 lectures later. So except that when you talk about the models oftentimes output a real number. So for example, if you think about logistic regression, the models output the logits, which could be anywhere on a real line. And then you turn that into a probability and then use that probability to compute a loss. And the loss becomes something, first of all, non-negative. And often, sometimes the loss is, reasonably, it's between 0 and 1. For logistic loss, it's not between 0 and 1, but I think the most interesting regime is that it's somewhat small, right? So it's between 0 and 1. And if you care about classification loss, then it's literally between 0 and 1. So the loss function sometimes has a scale in some sense, like it's something on the order of 1. But your model could be sometimes outputting some bigger numbers. So there is a conversion there, which will be more explicit in the future lectures. But beyond that, I don't distinguish them very much.
Gotcha. Yeah, I found it interesting that in the example, at least for binary classification, the complexity of the loss family was less than half of the complexity of the model family. Is it common that your complexity goes down when you compose it with the loss function?
I think it's common that they are related. We will see that in many cases they can be related, but I think I wouldn't read too much from that constant half, because this half does depend on how you define your labels. For example, if your label is 0, 1, I think you wouldn't see the half. So there's some small artifact there, right? So the constant. So it doesn't really matter that much.
Sure.
Okay, cool. Okay, let's continue. So we're going to prove this, and this is called symmetrization technique, the proof. And this is a very this is a technique that can be used in many other cases. Not necessarily in this course, but in other kind of like areas of probability, let's say. So symmetrization technique, I think it probably comes from those kind of areas of probability. Anyways, at the first place. So so the technique is that let's write down what we care about. So what we care about is the soup. I may not take expectation for now, just so that it's a little bit cleaner. We will take expectation in a bit. So this is not symmetric in some sense, because you have you have this subtraction here, and so these two terms don't look the same, right? That's what I mean by not symmetric. So there's a way to make them somehow more symmetric. So what you do is that if you fix, for now, let's say we fixed x1, z1 up to zn, and we let z1 prime and zn prime to be a different draw, another draw from the distribution P, RID. So you draw a sequence of copies of z1 up to zn, RID. And then what you can do is that you can write this second, the expectation, this quantity, using the zi prime. Just because by definition, all the zi's have the same distribution from P. So expectation of f is really the same as you look at expectation of sum of f of zi prime, because each of these terms has expectation the same as EF, and you average them, so you get E of f. Right? So, and you see that this already makes it a little bit more symmetric for whatever like just looks on the surface looks more symmetric, because this is a sum of things and this is a sum of things. Of course, it's still a little bit different because the expectation is in front of this thing, but there is no expectation in front of the first sum. What you can do is you can, of course, one thing you can do is you can put the expectation in front of the both term, which is not doing really anything, because for now zi is constant and zi prime is random. So in some sense, you are just putting some constant inside the expectation. And now, what happens is that you can switch the expectation with the soup. Maybe let's answer the question first.
Did you want that the sum between whatever and...
Oh, sure. Yeah, sorry. Is this one? Yeah, cool. Thanks. Yeah, so now we'll make it more symmetric. So we'll switch the expectation with the soup. So I'm claiming that if you switch them, you get an inequality. Zn prime soup. Right. So why this is true, and this is just a very generic inequality which claims that you can switch soup and expectation, get inequality. So generically, this is the claim is that suppose you have a function g that takes in two variables, and suppose you are taking expectation first over the randomness of the second variable, and then you take soup over the first and you take soup over the first variable. Suppose this is the quantity you have, then you can replace this by eventually by first taking expectation and then actually by first taking the soup and then take the expectation, right? Because when you do the math, you are doing it from right hand side to the left hand side. And why this is true? This is because you can have an intermediate step, which is you take soup over u, take expectation over v, and you bound this GUV by soup over u GUV. Maybe let's call it u prime. Right, so this inequality is very simple, it's just because this term is term-wise bounded by the soup. And once you do this soup, then you see that this whole thing doesn't depend on u anymore, right? So maybe I should have another step. So actually, I'm claiming that this is just equal to this, because this term doesn't depend on u. You already got rid of the u, right? So the soup over u just can be gone, and then the green term is equal to the term below just because you change the variable name u to u prime. That's nothing, right? So that's why it's equality. So in general, it's kind of like just probably useful to kind of know this as a fact, so you can switch the soup with expectation and get inequality. And sometimes I don't remember which direction of inequality it is, so that's why you still want to probably somewhat know how to prove it, so that in case you got confused which direction it is, you can still recover it. Okay, cool. So okay, so that's how this works. And now if you take expectation over z again, we already conditioned on z, but now suppose let's take expectation over z, then you see that this is kind of like very symmetric. So what we got is that you take expectation over z1 up to zn. And it's bounded by, now you have two expectations here. One is over z i's, and the other is over zi primes. And then you have soup. Let's put it into a single sum, by the way. Minus f zi prime. Okay. So now it becomes a little more symmetric. And I'll do one more thing to make it even more symmetric. So this one is symmetric in the sense that actually it's a mean zero random variable, right? It's not even mean zero, but actually in terms of distribution, the distribution is symmetric in the following sense. So fzi minus fzi prime has the same distribution as fzi prime minus fzi, because these two things are just the renaming of each other in some sense, so they have the same distribution. Or in other words, this has the same distribution as sigma I fzi minus fzi prime. For any sigma I, that is binary. Right. If it's -1, if it's +1, it's the same thing. If it's -1, you just flip the order. And right. So that means that you can, for free, introduce this random variable sigma I and not change anything. So that means that if you introduce this Rademacher random variable and you take expectation over sigma i's, you multiply the sigma I, this fzi minus fzi prime. So this is still equality. Actually, like here, even you choose any sigma I, this is equality. Of course, if you choose random sigma i's, and average them, it's still equality. Okay. So I think technically you claim that for any sigma I, this is equality. Technically, the first step is this is equality for every sigma I, for any sigma I. And then you say that even you take another expectation over sigma i's, this is still true. This is still true. And then you can switch the expectation in whatever you want. Okay, and I'm going to switch it just because it's a little bit convenient for me to do that. Okay. So now what I'm going to do is that I'm going to break this into two sums. So I'm going to have expectation. Here you have all the randomness. This is just a simplification of notation. So I'm claiming that this is less than sup of the first term plus the sup of the second term. And here, what we are doing is essentially exactly the same thing as the switch of the expectation, the swap of the expectation and the sup. But here we only have two terms, so it's a swap of sum and sup. So here we are doing something like sup of two terms. So something like a function of f plus another function of f over f, and then you can say that this is less than sup of f u of f. Sup u of f. I guess you can prove this, almost the same way as we have done with the expectation swap. It's just that you need one step in the middle. I will leave this as a exercise for you. So, and now probably you have seen that we are getting closer and closer to the definition of the Rademacher complexity. The only thing is that we have two terms, and the Rademacher complexity have just only of this. So now we can change this to we can swap the expectation with the sum, so you get sup di, and here and plus expectation sup minus sigma I fzi prime. And here the randomness is z1 up to zn and sigma 1 up to sigma n. So this is the first term is exactly Rademacher complexity. And I'm going to claim that the second term is also exactly Rademacher complexity, because here my randomness is z1 prime up to zn prime and sigma 1 up to sigma n. But again, because minus sigma I fzi prime has the same distribution as sigma I fzi, right? Because minus sigma I has the same distribution as sigma I, and zi prime has the same distribution as zi. So then the second term is still, this is equals to the first term. So basically this is just equals to 2 times this. It's 2 times the Rademacher complexity. Any questions?
It kind of feels like we just did algebra for like a bunch of lines. Is that? I don't know. It's just a question. Like that was a little weird. Like, did we prove anything really strong?
That's a great question, and that's exactly what I'm going to remark on. So the question was, if I phrase it slightly differently, so what we have really done here, did we do anything kind of like powerful, or did we do something? Because the left-hand side has a soup, the right-hand side still has a soup, right? So did we really do something really useful, or did we just do a bunch of algebra, right? So I'm going to claim that we did do something useful, and the reason is that the left-hand side, is something like a soup, is what we care about, right? The difference between the empirical mean and the population mean, right? So on the right-hand side, roughly speaking, the most important thing is this thing, right? So what we have achieved here. So one, we have achieved that we remove the EF, right? So we get rid of the EF, and it's probably not super clear why we should appreciate this fact that we get rid of the EF at the first sight. But I can say that this EF is is somewhat kind of annoying because you don't have a good control on it, right? So when you look at this, in some sense, this quantity doesn't depend on the relative. Like for example, this quantity doesn't depend on EF, right? So if you shift it a little bit, it wouldn't change. Actually, we're going to claim that this quantity, the right-hand side, is translation invariant. So in some sense, you remove the translation invariant part. So maybe let me just claim the right-hand side is translation invariant. Or maybe the Rademacher complexity. I'm going to claim that, prove this in a moment. Let me see whether I plan to do this in today's lecture. I think I didn't plan to do it today's lecture, but this is a claim. So in some sense, you remove the translation invariant part, you remove the EF, right? So which is useful in many cases. And second, you sometimes introduce more randomness. Sigma 1 up to sigma n. So why introducing this randomness is useful? It's probably still unclear right now, but eventually what we're going to do is that we are going to have, so currently what we really have is you have an expectation of this, right? You also have the expectation of this. And here the randomness is z1 up to zn and sigma 1 up to sigma n, right? So we will introduce additional randomness, and this will allow us to drop the randomness from z1 up to zn. This will be something we'll see, I guess, probably in the next lecture. So eventually you don't have to care about you don't have to take expectation over z1 up to zn. you can claim with high probability. So the right-hand side wouldn't have the run like z1 up to zn. You don't need to take expectation over z1 up to zn, and the only randomness comes from the sigma i's, which if you eventually, I guess probably you don't see exactly what I mean, but if you eventually you only care about the randomness of sigma 1 up to sigma I, sigma 1 up to sigma n, that seems to be a benefit, because this is a very much simpler randomness, right? So sigma up to sigma n has a very simple distribution. They are just Rademacher random variables. So they are much less complicated than the distribution of z1 up to zn, which is something you don't know, right? You just assume there's a distribution p, but you didn't really know any other properties about it. So I think that's the second benefit. But of course, the limitation is that we still have the soup, which is still a problem. But I think you probably shouldn't expect that you can remove the soup on this level when you have an abstract family class. You probably shouldn't expect you can remove the soup completely, right? So it should be the next level where you remove the soup when you have a concrete hypothesis class. Cool. So the next part is another useful property or kind of useful thing to know about Rademacher complexity, which is that this Rademacher complexity can depend on the distribution P. It still can depend on distribution P, even though our goal is to try to kind of like use the new randomness, right? Deal with the simpler randomness, right? Why this is the case? This is just because in this definition of Rademacher complexity, you do have to draw some z1 up to zn from the distribution P, right? So this is a gym example where you can see that where P is a point mice. So let's say Z is always equal to Z0 almost surely. So whatever how you draw it, you always just draw a single point. And in this case, actually, you can have a good Rademacher complexity bound for any bounded function. So suppose, let's say -1. Suppose you care about f in F. And this is the only constraint on the family F. So basically, you care about F, or maybe more tech. Let's say F is the family of functions F such that Fz0 is bounded by 1. So you just have a bounded family of functions. You don't even have any parametric form. Still, you can prove that the Rademacher complexity of this family is small. So you can say that if you look at soup, so this is what? Because Fzi is always the same. So this is literally equals to 1 over n times Fz0 times sum of sigma I. And because Fz0 is just a constant, it doesn't depend on what F is, right? Because Z0 is, wait, sorry, my bad. So F, I'm wrong with that. So Fz0 is still depends on Z0, right? But Fz0 is bounded between 0 and 1. Between -1 and 1. So that means that this is less than or equal to expectation. If you just bound this Fz0 by 1, you get 1 over n times sum of sigma I, absolute value. Right. So, and this is actually, then you use Cauchy-Schwarz or use the, I think this is called Cauchy-Schwarz. So the expectation of this random variable is smaller than the expectation of the square of the random variable to the power half. And then you can, actually these derivations, we're going to see this kind of derivation several times. So you get a half expectation sum of sigma I sigma j. I is not equals to j plus sum of sigma I square times 1 over n square. Right, I'm just expanding expanding it. So you get 1 over n squared. Sigma I, sigma j has mean 0. So you get sum over I from 1 to n expectation sigma I squared a half. So this is, each of this is 1. You take the sum, it get n. So you get 1 over n to the power half. This is 1 over squared. So in some sense, this is kind of like interesting, right? So like for a very, very large family of functions without even parametric form, you can still have a good Rademacher complexity. And the reason is that the distribution is so simple. So it's, in some sense, this is an indicator that the Rademacher complexity can capture something about the distribution, right? If your distribution is extremely simple, then Rademacher complexity can capture that and tell you that it's very easy to generalize, right? Right. So basically, any f on a very simple distribution should be considered as very simple, even though this, in some sense, this family of f is just, you have basically no assumptions on f in some sense. Right? There is no parametric form. It's a very large family of functions, but with respect to the distribution, the simple distribution, it should be considered as simple. And this is what Rademacher complexity can tell you. So that's saying that Rademacher complexity can take into account the distribution P. But how much it can take into account of the distribution P, that's a question mark, right? So in many of the other analysis, you don't, like in manual analysis, you don't have this property, like you don't really use too much about the distribution P in many of the concrete bounds for Rademacher complexity. But in principle, it can capture something about P. I have 15 minutes. I think there's time for me to do this next part. Let me see. Yes, I think I have time to do this. Okay. So the next part, if there's no questions.
Once you know that the different independence so let's say you know that getting the other thing. Like, I mean, is it possible to use that information to get that?
So your question is whether, for example, when the features x, the coordinates of x have correlations, or maybe have independence. Independence is probably, it's more like a simplistic thing, right? So can you get a better bound from Rademacher complexity? I think to answer this question, we need to zoom into concrete settings, right? For linear models, I guess you see that you would get bound, at least if you compare two extreme cases, right? In one case, all the coordinates are correlated, and the other case is that actually it's unclear, right? So because if all the coordinates are correlated, actually you probably should have a better bound, because if, for example, in a very, very extreme case, right, so all the coordinates are the same, then you effectively have a one-dimensional problem, so you should have a better bound. So it does depend on the particular situation, I think. Right. So yeah, so it's interesting, right? It's not clear that independence means really simpler. Independence could mean that it's more complicated. Just because when you have independent input distribution, right? So you have a diverse set of distribution, diverse set of data. It might be even more hard. It's harder to generalize in some cases, right? So, for example, here in this one point mass case, right, you have a very narrow family of data. It means you can generalize easier because you can just memorize that Z0, right? So independence might make it harder. Okay, so the next 10 to 15 minutes, let me try to define this so-called empirical Rademacher complexity. And the goal here is to remove that expectation in front of the soup, right? So currently the average version has two expectations. One is over the randomness of Z1 up to Zn, and there's another expectation over the randomness that we created, right, over sigma 1 up to sigma n, and you have this soup. And we're going to claim that this is basically similar to this, without expectation, with high probability. So with high probability, and the probability is over the randomness of Z1 up to Zn, right? So you have to draw Z1 up to Zn, but for most of the choice of Z1 up to Zn, these two things are similar. Right, so this is a random variable that depends on Z1 up to Zn. And this is a random. This is just a constant. Right, this number is not a random number. I probably shouldn't call it constant. This is a deterministic number. Right, so this number depends on Z1 up to Zn, and I'm claiming that the second one, the right-hand side, is concentrating around the first one with high probability. So, and if you can do this, then that's what I kind of alluded to before, right? So now, if this is defined to be empirical Rademacher complexity, I guess let me have a notation for that. This is called. I think let me just. I think in the notes there's a formal definition, but here let me just, for the sake of time, let's just define this to be Rs of F, where S is the set of Z1 up to Zn. And this is called empirical Rademacher complexity. And you can see that the original Rademacher complexity, the average Rademacher complexity, is the expectation of the empirical Rademacher complexity, where you take expectation over the set S, right? So just because these two things only differ by a single expectation. And so if you can do this, then you have a high probability bound. You don't have to average over Z1 up to Zn. And also you can do the same thing for the left-hand side for the uniform convergence thing, right? So recall that before we only proved that the expectation of Z1 up to Zn soup this minus EF, right? We want to prove that this is less than Rademacher complexity, right? So this one, we'll also show that this is approximately equals to this with high probability. Like I guess I should say the later one. This one, later one, is a random variable, right? That depends on Z1 up to Zn, is approximately equal to the expectation with high probability. So if you have both of this, then you basically remove the expectation from your equation and you get a high probability bound. Does that make sense? Any questions? Okay. So basically, eventually we're going to prove this. So let me state a formal theorem. We can prove that you assume all the F's are bounded, then with probability at least 1 minus delta, we have the soup. So here I don't have expectation. This is the, but there's a random over the randomness. Of Z1 up to Zn. The soup of this is less than 2 times the empirical Rademacher complexity instead of the average Rademacher complexity plus additional cost, additional term, which is the log of 2 over delta over 2n. So you pay additional small term, which is on the order of 1 over square root n times something logarithmic in the probability delta. But basically by paying this, you get a high probability bound instead of an average version. I think the proof is actually relatively straightforward. It's basically just applying McDermott inequality. But maybe let me do that in the next lecture. I think it takes probably 10 minutes. Maybe let me start with the remark, right? So I guess typically this ln 2 delta over n, this is typically much smaller than either the Rademacher complexity or either the empirical one or the population one. And the reason is that these two things will be something like square root something over n. And this something depends on the complexity of f. It's something that is not negligible. But here you have square root some logarithmic term over n. So that's pretty much the smallest thing you can think of, right? So like a logarithmic is kind of like a constant. So your complexity of f wouldn't be on the logarithmic of anything. It should be something bigger than that. So that's why typically this additional term is negligible. So that's why basically you can think of this, you didn't lose anything by doing the empirical version. And it's interesting that what you lose here, at least on this level, what you lose here doesn't depend on complexity of f, right? So basically, if you so this term depends on complexity of f, but what you lose here between the expected empirical and population don't depend on complexity of f. And maybe I think this is a perfect time for doing the second remark, remark 2. So, and I guess RNF or RSF, they are both translation invariant. So, what does that mean? That means that suppose you have f prime, which is equals to a translation of f, which means that this is a family of function f prime z, which is equals to fz plus a universal constant c0. Right, so for every function in capital F, you have got a function in capital F prime, which is just a translation. You just add some c0 to it. Then they have the same empirical Rademacher complexity. And in some sense, we have seen this derivation somewhere in one of the derivations before, but let me just make it more explicit. So the Rademacher complex of this is you look at the expectation of sigma, and you take the sup of sum of sigma I f I prime f prime ci. And you plug in a definition. Plus C0. Right. So now you can put the part about C0. I think we have seen the same technique before, because C0 is not a function of little f. So you can put it out. So you get plus 1 over n times sum of sigma I times C0. And then you can swap expectation with the sum. So you get expectation sigma the sup plus expectation of 1 over n times sum of sigma I C0. And this becomes 0 because sigma I is a binary, is a Rademacher random variable. So then this is Rs of f. So in some sense, this is a property of the Rademacher complexity, which is somewhat interesting, right? Like you don't care about the translation, but you do care about the scale. So if you scale everything by half or by 2, then you would change the Rademacher complexity, but it wouldn't change when you shift things. So it's about the relative differences between functions in f. It's not about the absolute size of f, right? So for example, if the function of f always takes values between 1000 and 1001, that's not very different from taking values between 0 and 1. Okay, I think this is a natural stopping point for today. Any questions? First of all, it's not always the case that, right? That's a good question, right? So I claim this, vaguely without any justification. So why the Rademacher complexity should be like this, right? 1 over square root n. So I think it's not even. So I should say it's not actually exactly true. Like so for most of the cases, actually for all the cases we are going to see in the lectures, it's 1 over square root n. But in some cases, it could be the dependency on n could be a little bit different. So yeah, so sorry, I was not quite clear. And I think I'm not sure whether that question is still in the homework. I think in the homework question, there used to be a question where you have other dependency on. I think I probably removed that question for this year. I remember I removed it just because it's not that relevant to the overall goal. But it could be other dependencies. For some reason, it's always like, it's mostly the case is 1 over square root n. I think the reason is that even you look at a single example, you don't take the sup, right? You just look at you do the wrong thing, right? So you say, I fixed my function and then I draw my data. I look at how different the empirical one is different from the population one, right? That's always 1 over square root n, like without any dot. Right, so that's why you can never go better than 1 over square root n, but you can be worse than 1 over square root n. I'm not sure whether that makes sense. Right, so even you look at the concentration of a single f, right? Like you fix the function h, you draw the random variable z1 up to zn, you still have some fluctuation on the order of 1 over square root n, so you cannot beat that, but you could be worse than that. From definition of the Rademacher, I think you can still see that to some extent, because if you look at the sum of sigma I fi, maybe let's just here, right? So this is still a sum of n terms, right? And each of, so like even you don't take the sup, this term would be something on the order of 1 over square root n, just because of the concentration. You have sum of n terms, each of them is on the order of 1, and so the sum of the n terms is on the order of square root n, and then you divide by n, you get 1 over square root n. We can talk more offline maybe. Okay, sounds good. I guess I'll see you on Wednesday.